I meant to say when we had that fruitful disagreement in Yale, where I first realized what an amazing person Rob was. But I guess the only person who hasn't been thanked is Carl Hafer, so I ask us all to do that. Okay, so I have the longest title, that's for sure. Historical Philosophical Reflections, etc. Newtonian, Kantian, and Einsteinian Relativity. This is not a familiar way of talking. This begins with work that George Smith has been doing, and he's written a paper called Newtonian Relativity, a feature of which is that it gives at least equal weight, and in a way more weight, to Corollary 6 of the Principia of to the laws of motion than to Corollary 5, where Corollary 5 is Galilean relativity, Corollary 6 is the extension to acceleration, which is what has to do with the principle of equivalence in Newton. And what I want to do is start by just saying a little bit about Newtonian relativity, and then show how in different ways it continues with Kant's comments on Newton and his own way of taking Newton, and then trying to see how that goes in some kind of continuous narrative into Einsteinian relativity, the most familiar notion. So, begin with Newton. So there's the Principia. And here are the two corollaries I just mentioned. When bodies are enclosed in a given space, their motions with respect to one another, or their motions what inter se, among one another, George has emphasized, are the same whether the space is at rest or whether it is moving uniformly straight forward without circular motion. That's what we call Galilean relativity, Corollary 6. If bodies are moving in any way whatsoever among one another, inter se, and are urged by equal accelerative forces along parallel lines, if they're all, as it were, falling together, they will all continue to move with respect to one another in the same way as if they would if they were not acted on by those forces. So this is a little bit like Einstein's elevator. Imagine the elevator is falling with some kind of constant acceleration for all the bodies, a la Galileo. In some sense, you can think of that as canceling maybe the gravitational field, or doing something to these to the actions of the bodies with respect to one another, so that it's as if there wasn't a gravitational field. Okay. The main interesting example of this in Newton's applications is to Jupiter and its moons, and also to Saturn and its moons, but I don't have that in this picture. This is Galileo's picture of the solar system, and of course the Copernican version of it in the dialogue concerning the two world systems. So here you see his favorite moons, the Galilean moons. And the idea is this is one of those falling systems, falling toward the sun, with all with the same acceleration, very nearly parallel lines. And what that means, as we would put it, is that you can take the interactions that are happening between Jupiter and its moons to be as if they were happening in an inertial frame, regardless of this fact that they're all falling toward the sun. Okay? And I just want to emphasize here that this is a crucial beginning of what George thinks about in Newtonian relativity, but this was actually first emphasized by Rob in his book, Understanding Space-Time, and here you see the Galilean moons all falling toward the sun, which is a main example for him, and precisely the point that we can treat this as an inertial frame as far as the motions within the system are concerned is a crucial thing that Rob uses to explain the kind of relativity there is in Newton's theory. I invite you, however, to look at this picture that was not due to Rob, but I think Rob, his story is that he gave the correct picture to the person who designed the cover, and there are 4 orbits here, and there are 4 moons here. But there's no moon on this orbit, and there's 2 moons on that. So this is Eo's orbit, what we call Io, and somehow Io got moved up into the same orbit as Europa. Okay, so that's weird. Rob tells me that his son, when he was 7 years old, said, "Dad, why are there 2 moons on one orbit?" And so we knew something about that boy. I only noticed it actually when I made this slide. Okay, so there's that. Now, natural question is, what about this little system here? This is the Earth with its moon. Does the Earth and its moon satisfy this Corollary 6 the way that Jupiter and the Galilean moons does? Well, actually not. You can't really tell from this picture because the Galileo's picture, I mean, they're very close together. The orbit of the moon is drawn so that it's not the size of Io's orbit, which is what it really is, but almost as big as Callisto's orbit. So you don't really see the difference in, as it were, parallelism or almost parallelism there. But if you look at it to scale, you get a better idea. I don't have the moons here, but here we all know this. It's about 100 million miles from the sun to the Earth. It's about 500 million miles to Jupiter and so forth. So this is much further. Now, the way these moons are arranged is that Io is about the same distance from Jupiter as the moon is from the Earth. That is 250,000. Callisto, the most distant, is about 1 million miles away, and so the other ones have intermediate distances. It's not immediately clear from those facts exactly how all that parallelism is going to work out. I think one also has to take into account, and people can correct me if I'm wrong, that the gravitational field of the sun is going to be a lot weaker when you get to Jupiter. And of course, Jupiter's gravitational field is much, much stronger than the Earth's. I think that probably plays a role. And the story that George tells is how Flamsteed asked Newton, how come there's so many problems with the moon's orbit, but we don't have any problems with Jupiter and Saturn? Those behave just beautifully. And it has to do with corollary 6 and the way in which it can approximately hold in one place or another. Okay? So let's go back about how this shows up in the Principia. So now we're in book 3. Phenomena 1, phenomena 2, these are both what he does with the circumjovial planets, that is Jupiter's moons, Saturn's moons, and the phenomena, that is the observed phenomena, according to Flamsteed and to Cassini, are that by radii drawn to the center describe areas proportional to times, that is Kepler's second law, and their periodic times, the fixed stars taken to be at rest, are as the 3/2 power of their distance from the center, the third or harmonic Keplerian law. Same thing for Saturn. So that's indicating the kind of regularity you see there. Now we get to the moon. The moon, by a radius drawn to the center of the Earth, describes areas proportional to the times. That's the second law. But there isn't anything about this 3/2 power law, partly because there's only one moon. But it's also because, as we'll see in a moment, the inverse square law gets a little bit screwed up here. And what Newton says when he introduces the phenomena, actually the motion of the moon is somewhat perturbed by the force of the sun. But in these phenomena, I pay no attention to minute errors that are negligible. So he's already indicating that what he's saying isn't exact here. There's going to be a correction. The correction is ultimately going to have to do by, you have to take into account to the sun's perturbation of what's going on with the Earth and the moon. And that comes out when Newton describes the inferences from these phenomena. So here we get the inverse square force following from the harmonic law, Kepler's harmonic law. And here he does something quite different when he gets to the moon. And then, of course, he does things with the planets, too, in between. I won't say anything about that. Here, the force by which the moon is maintained in its orbit is directed toward the Earth and is inversely as the square of the distance of its places from the Earth. So far, it looks like it's the same thing here. The second part, that is the inverse square, is evident from the very slow motion of the moon's apogee. So this is a different phenomena than the harmonic Kepler's harmonic law. Again, partly because there's no other moons there. But actually, what Newton proves is that if you're looking at possible exponents for a centripetal force, the only one that's going to give you a completely stable orbit with no precession is going to be inverse square. And here we get a small deviation from that. But because it's very small, he says we can take it to be inverse square. Then he goes on to have a calculation to say, well, actually, when we do a calculation by observing what's going on, it's a little bit greater than 2, the exponent. And Bill can tell you exactly what the number is.
Sorry, I can't offhand.
I'm shocked. Okay. That's just a joke, because Bill usually loves to give those things. Okay. It's really, it's like 1 over 252 or...
2 over 243.
Yes! 2 over 240. Okay, good. Now, this motion of the apogee arises from the action of the sun. Newton hasn't shown that here in any way, as will be pointed out below. So when he talks about the three-body problem, he attempts to show this, not successfully, however, and accordingly is to be ignored here. So there already something is very different happening here. Just call your attention to that. Now we get to the moon test in proposition 4, which one of the things it does is it makes the moon-Earth system, by linking it to the falling bodies near the Earth with their Galilean uniform acceleration, part of a single system, possibly a system that has other moons in it or other possible moons' orbits in it, all of which are governed by the same inverse square field from the top to the bottom. Right? The thing about the 3/2 power law, as opposed to, say, using the ellipse to infer 1 over r squared, or even the thing about the motion of the apogee for a single orbit, is that this says something about how the same inverse square holds from orbit to orbit, from top to bottom, which is a crucial property here. Okay? So this makes it look like something like the 3/2 power law ideally would hold here. But all Newton has shown is that if you take this acceleration to be the same as the acceleration that we've observed pretty closely for the moon, and we let that just drop down to the center of the Earth, when it's at the surface of the Earth, it will have the same value as little g. Okay? So it really hasn't shown the way he has for the other moon systems, Jupiter and Saturn, but good enough. This is the argument for that holding here. All right. Now, one fact I now want to emphasize here is that there are 3 different types of mass in Newtonian theory, which are integral to a kind of way of thinking about the principle of equivalence holding here. What we now call passive gravitational mass. The M2 is now the moon that's being attracted, and M1 is the primary body that's attracting it. This mass of M2 drops out, and the acceleration can be reckoned independently of it. And that involves the equality between what we here call passive gravitational mass and inertial mass, namely the mass that occurs in F equals ma for any force. This only holds for gravitational force. And we get down here, we see this property that gravity has but other forces don't have, and that not only is the field, say, inverse square like the Coulomb field would be, but the acceleration is inverse square because of this way that inertial and gravitational mass relate. The coupling constant, as it were, is just the inertial mass, and so we just have a field for the acceleration itself, meaning that all bodies are going to accelerate in the same gravitational field. Here, M1, which is the mass of the primary body doing the attracting, we call that active gravitational mass. Well, I'll come back to that. But what matters here is that for this Galilean acceleration field property, which this is a terminology introduced by Howard Stein, it's the equality of these two that you need. Okay. All right, so now I'm going to draw a few morals from this very brief sketch of that. First, corollary 6 provides criteria for what George Smith calls a quasi-isolated system, meaning a system within which the motions of bodies in that system, inter se, can be entirely accounted for by forces between those bodies, ignoring the other bodies. The criteria are satisfied only approximately. For example, they involve parallelism, which in general is only going to be very approximate, and so on. But when those criteria hold, you can infer that the motions can be accounted for, to very, very, very high approximation by not looking at anything outside the system. So for the moons of Jupiter, the moons of Saturn, you can do that. Okay? Applying corollary, this is what I just said, applying corollary 6 this way within the solar system assumes the quality of inertia and passive gravitational mass. This property is established by appeal to Kepler's third harmonic law or to an analog thereof as in the moon test. The Earth-Moon system, however, fails to be quasi-isolated. Perturbations by the sun must be taken into account, otherwise you get this 1 over 202, right, you get that funny small addition to the exponent 2. Perturbations of the sun must be taken into account by approximative reasoning in the Newtonian style. That is, trying to really calculate what the effect of the sun is. Newton couldn't quite do that. A process that is only successfully completed by Euler and Clairaut in the late 1740s after Newton is dead. Now let me just note that this notion of approximative reasoning is a much stronger and interesting one than what's happening up here, right? Because this is just a way of saying that when the parallelism is close enough, and when the gravitational fields of the sun and the other body are out of sync enough, that is, the other one is much bigger at that point, then you can just treat it as a quasi-isolated system. This is much more interesting because it leads to a methodological process, one that I think Bill was talking about yesterday, whereby you have to keep looking for the forces that are outside, because you already know that it isn't quite working the way you wanted it to work. So you can either throw up your hands, or you can say, well, no, I'm going to look for perturbations that are also governed by gravity, in this simple case involving the sun, but that turns out not to be simple at all. Finally, it's worked out. Well, of course, there are other perturbations by the planets on each other, and all kinds of things that keep happening within the solar system. Newton's program is to keep using the law of universal gravitation applied to finer and finer details or finer and finer anomalies until ideally they would all fall out, and universal gravity at that point, Newton's law, would be, as it were, completely vindicated, at least within the solar system. Now, of course, as we know, eventually this breaks down with Mercury, and that's Einstein comes in there, and that is going to be an interesting feature we'll come back to later. Okay, so with Newton, I'm going to switch to Kantian relativity. And one of the things I'm interested in is there is a kind of relativity in Kant, and as we'll see, it more or less involves, Kant emphasizes corollary 6 a lot without explicitly mentioning it. Corollary 5, he doesn't acknowledge. Oh, and you'll see what's going on with that in a moment. And there's a certain way in which, by the way he applies corollary 6 and other things he says, the kind of approximative reasoning that can take place within Newtonian gravitational theory is perfectly okay by Kant. Now, of course, when you get to Mercury and the Newtonian theory breaks down, then there's a problem for Kant, especially if that involves giving space itself a non-Euclidean geometry, as it does. Okay? That's something that can't happen according to Kant's view of pure intuition. So we'll come back to that. So his view is no corollary 5, and corollary 6 is applied implicitly, crucially, as we'll see. So what's going on with this no corollary 5? What's wrong with Kant? Okay, well, the way Kant thinks of relativity basically is this. What is absolute space for Kant? Well, the idea is we start with a frame of reference, a parochial frame of reference where we are, fixed on the Earth. We look up and we derive something like the Ptolemaic system, which is the true description relative to that point of view. Okay? And then what we want to do is keep moving to wider and wider rotating systems where we get better and better descriptions than this one. So we first go to the center of the mass of the solar system, not quite the center of the sun, a la Newton Book 3. And now that gives us a frame of reference in which the frame of reference that we started with taking the Earth to be at rest, is a little part, and embeds it into a better frame of reference, which is got its center at the center of mass of the solar system. Okay? Now, Kant is one of the first people to get into the idea of the Milky Way and realize and to assert that the Milky Way itself is just a part of a bigger, the solar system is just a part of a bigger rotating system, namely the Milky Way. All this first happens actually in 1755 in Kant's universal theory of the heavens, and in there he's often credited with being one of the founders of the nebular hypothesis. But then for Kant, so there's the Milky Way. That's not enough. Kant thinks that the Milky Way, he thinks this is just going to keep on happening. Right? The Milky Way is going to be a part of a bigger rotating system of other galaxies, something like this, and so on ad infinitum. We never get to an end of this. So what absolute space is, according to Kant, is what you would find in the limit, or what we're, more precisely, what we are approximating step by step, but never reaching in the limit, by moving out through this ever expanded sequence of rotating systems that are each one nested within the other one. So we kind of do a Book 3 kind of argument starting with the Earth, and then we do it again for the solar system relative to the Milky Way. We do it again relative to the Milky Way, relative to some bigger system, and so on. We never get to absolute space, but that's the only thing it could mean, as it were, empirically, according to Kant. And it's because of this picture that he's both putting an emphasis on corollary 6, as we'll see in a minute, and why there's actually no room for corollary 5, because when you think about it, if you got to that center of gravity of the entire universe, which you don't, that thing is just going to be at rest, according to Kant, because that's how you define the true motions, is relative to whatever the center of gravity of the appropriate system is. So far, so good? Okay. So here's what he says in the general remark to phenomenology, the last chapter of the Metaphysical Foundations of Natural Science. And he says, well, the only thing that would be absolute motion is if you had motion of a body that was not in any relation to any other body in its motion. Okay? The only thing that could be absolute motion then would be the rectilinear motion of the cosmos. That is the system of all matter. And of course, that's a kind of ideal object for him. We never have that, but we try to approximate to it. This is related to his antinomies. Right? And then he goes on to say any proof of a law of motion, which amounts to showing that its opposite, that is, it's contradictory, would have to result in a rectilinear motion of the entire cosmic system, is an apodictic proof of its truth, simply because absolute motion would follow, which is utterly impossible. That is, the motion of the center of gravity of everything. Okay? The law of motion he has in mind here is the law of action and reaction. Okay? So the law of action and reaction, I'm kind of jumping ahead, and I'll come back to it. For Kant, that's just proved by saying we consider two interacting bodies. How do we define their true motions, roughly? Well, we start by taking it to be the motions relative to its center of mass. That's the only way you can think about the true motions. So this is why he denies that a rectilinear motion of the center of gravity is possible. That would be a motion that's not defined relative to anything empirical.
Mike?
Yo.
But for Kant, with all these bigger and bigger systems always going to be rotating around their center of mass?
They all are going to be rotating around their center of mass. And actually, another sentence or two down, he says, the rotation of the whole thing is not impossible. It's different from the rectilinear motion. Although we don't have a reason to assume that for the, as it were, limit, he says. So. Okay. Now, this is quite different from the way Newton deploys corollary 5 in his argumentation. First, he has corollary 4, even before corollary 5, where he's considering center of gravity ideas, and he infers, basically by the same reasoning as corollary 5, the common center of gravity of all bodies acting upon one another, excluding external actions, either is at rest or moves uniformly straight forward. Not that it's at rest, but it's either one. Kant is saying it's at rest necessarily. That's the difference about Galilean relativity. And when Newton comes to show in proposition 11 of book 3 that the common center of gravity of the Earth, the Sun, and all the planets is at rest, and remember, for Newton, that point is always very close to the center of the Sun because its mass is so much huger than the other masses. Okay? The reasoning is that center by corollary 4 is either at rest or will move uniformly straight forward. Okay, fine. But he's assumed as a hypothesis that the center of the system of the world is at rest. And by that he means the solar system, the different world systems. Everybody agrees about that. It's just a hypothesis. It's not a proof of anything. But if that center moves down here, the center of the universe would also move contrary to what everybody has agreed upon. Kant doesn't reason this way at all because he takes it to be a necessary feature of the notion of the true motions and the notion of absolute space, insofar as we can make empirical sense of it, is that it just is that center of gravity. Okay. So, provisional morals, Kant and Newton. Although Kant does not acknowledge corollary 5, and I think we now see why he doesn't, he uses corollary 6 implicitly to move through an indefinitely extended sequence of nested rotating systems, each of which is treated as, I put approximately quasi-isolated, to include the Earth-Moon system, since he starts at the Earth. Absolute space for Kant is the regulative idea. That's his official name for what kind of thing this is, right? Rather than a pure concept of the understanding, which is constitutive, meaning you can find and instantiate it in experience. So in experience, there are substances, there are causes, there are interactions, but in experience, there ain't no absolute space. The best we can do is approximate it in the infinite limit that we never reach. According to the relativity principle explicitly formulates, and we'll look at that in a minute, proposition 1 of the, again, last chapter, that's the one about the true motions. We can begin the procedure for determining the true motions from any planet in the solar system that has moons. So that could be, or from the, we could begin it from the sun if we if it wasn't too hot, right? So we can begin it, we can and do begin it from the Earth, and that's going to have to just be an approximately quasi-isolated system in terms of the moon. Or we could begin it with Jupiter and Saturn. Right? The same argument's going to hold. We can do the moon tests, we can do everything. Okay. He does not, Kant, discuss the asymmetry anywhere, as far as I know, between the Earth-Moon system and that of Jupiter and Saturn. So he doesn't make the point that it's only approximately quasi-isolated. He doesn't discuss the kind of corrections that have to be made, although, as I'll indicate in a moment, he's perfectly open to those kinds of corrections. So this is the closest he comes to establishing what might look like the principle of Galilean relativity. And in most of the Kant literature, especially by people who know something about physics, they take this to be Galilean relativity. The rectilinear motion of a matter with respect to an empirical space, as distinct from the opposite motion of the space, that is a relative space, a reference frame, is a merely possible predicate. So people have often said, and the temptation is quite strong, this is Galilean relativity that Kant is stating, ignoring the fact that he doesn't say rectilinear and with constant speed. He doesn't say uniform rectilinear. But he does know the difference between uniform rectilinear and non-uniform rectilinear. He makes that distinction in other parts of the book. Okay. Also, this is odd. The same when thought in relation to no relation at all to matter external, that is absolute motion, is impossible. Well, again, according to Newton's corollary 5, it would be possible, physically possible, and only some kind of more or less arbitrary hypothesis would rule it out, as we just saw. And here's now his proof of this. I'm just going to give you a little piece of it. And I'm just going to call attention to this part of it. This is kind of the argument for what he's saying. If the observer locates himself in that space, one that's taken to be at rest, the body that's moving relative to it counts as moved with him. If he so suppose he's locating himself in the Earth. Suppose he's locating himself in the sun. If he locates himself, at least in thought, in another space, comprehending the first, say the center of mass of the solar system, relative to which the body is likewise at rest, then that relative space counts as moved. So he's just saying it depends on where you start, where the observer is going to start their quest for the true motions. And what I think Kant has in mind, and I think I've made a pretty good case for this, is this kind of thing in the Principia. Phenomena 4, this is when he's talking not about Jupiter, not about Saturn, not about the Earth and the Moon, but about the Sun and the planets. And interestingly, what he says here, and people who know Newton all know this very well, he wants to leave it open between the Tychonic and the Ptolemaic system. Newton's very clear about it. And then he wants to solve that in these propositions. He wants to give the answer. But the phenomena is stated such that we could either take the sun as at rest and the planets and the Earth moving about it, or we could take the Earth as at rest and let the sun rotate around the Earth and everything else rotate around the sun, because the phenomena show that it has to be that way. Okay. And then in proposition 11, he gets to the common center of gravity of the Earth, the sun, and all the planets is at rest. That's how we can move beyond this. The sun is engaged. The sun is also in motion because it doesn't have infinite mass, but since its mass is so much larger, this is the solution now to the world systems problem. Okay? So I take this to be paradigmatic of how Kant starts with something that satisfies that relativity principle in proposition 1. Rectilinear motions, and we'll see what I mean by that in a moment, can be given either to the sun or to the Earth. But the way you get rid of that arbitrariness is by looking for the common center. Okay. So it's something quite different from Galilean relativity. And what the moral is, I think, is that for Kant, any two interacting bodies have a true as opposed to a merely apparent acceleration towards one another. They have an impact too, according to Kant, but let's think of the paradigmatic case as being bodies falling toward each other gravitationally. So the Earth and the sun have those accelerations. Of course, they also have this inertial component, and they have an orbit. But he's talking about the accelerations. And it's in terms of that center of mass within which the accelerative forces are viewed that we define the true center of motion. Okay, and so again, this is what I mentioned before. Proposition 4 of the mechanics, the third chapter. In all communication of motion, action and reaction are equal. He simply proves that by saying the true motions and the true forces are all going to be defined relative to this center of gravity. And he makes a remark saying, Newton by no means dared to prove this law a priori, that is, action-reaction, and appealed to experience, for example, to pendulum experiments in the scholium to the laws of motion. And Kant seems to be disapproving of that move of Newton's. It should have been established a priori this way as a necessary condition for defining the true motions empirically in the first place. So that I take it to be what's going on in the proposition 1. It's a move from equal, not equal, but equal and opposite changes of momentum of the two accelerating interacting bodies, followed by a determination of the center of gravity to resolve any ambiguities. Now, there's another place where Kant seems to be criticizing Newton, which I have often emphasized in the past and made a big deal about, and I now think I was wrong to make a big deal about it, so many of you are going to be happy. Here's what Kant says. First, in proposition 7 of the dynamics, he has a proposition that says the attraction essential to all matter, so he's saying gravity is essential to all matter, is an immediate action of it on others through empty space, action at a distance. And Newton and everybody is wrong if they have doubts about action at a distance. Right? Newton is set at variance with himself if he or his contemporaries, perhaps even Newton himself, Kant says, want to leave it open that there could be some kind of mechanism that isn't an action at a distance explaining this gravitational attraction. And the reason Kant gives for this being a problem is that if you say that, then you're going to have a problem with this fundamental feature of Newton's argument, namely that the attractive forces of two planets, e.g. Jupiter and Saturn, manifested at equal distances on their satellites, are proportional to the quantity of matter of these heavenly bodies. That means you're using these accelerative forces to measure the quantities of matter of the attracting bodies, the primary bodies. This is now the active gravitational mass part. And what Kant is saying is that that part's not going to happen unless you somehow accept this proposition 7. Okay? And in saying Newton might be set at variance with himself, this can be taken as a critical remark, although I think it's not as much as I once thought. And we'll see in a minute why. But what is Kant talking about more specifically? Okay, so remember we had the acceleration field property that involves the inverse square law holding from orbit to orbit, the harmonic law, and the equality of passive gravitational and inertial mass. Okay? Now what we want to do is see how do we establish the equality between inertial mass and this active gravitational mass of A. So now what we just know, I'm not going to assume it, I'm just going to say we know there's some constant, which now we take to be, big G times the active gravitational mass, but now what we want to do is just derive it from this acceleration field property. And the setup is basically this with Jupiter and Saturn. Okay? So each one of these is going to satisfy relative to one of its moons this acceleration field property. Okay? And if we assume that the gravitational field of Saturn extends to Jupiter and vice versa, then this is going to fall towards Saturn using the same acceleration field as the moons of Saturn. And Saturn is also going to fall towards Jupiter using the same acceleration field of Jupiter as the one that acts on its moons. I hope I said that properly. Okay, so that involves extending the gravitational field way beyond the moons. And so that means going against a kind of explanation for each moon. Okay? That's going to block this argument. Now, and the idea is the argument proceeds by applying action and reaction directly between Jupiter and Saturn. Right? That's this. Okay? And now we plug that into these things. Right? You do this very simple calculation, and you get that the mass of Saturn is to the mass of Jupiter as this constant, the acceleration field constant in Saturn is to the acceleration field constant of Jupiter. And therefore, so that's the same as saying there's a constant such that k is g times that constant. Okay? So that now we've recovered what we would call the law of universal gravitation, and we've established the equality of active gravitational and inertial mass. Inertial mass is what's happening here. This is the inertial mass of the laws of motion, which hold for any force. Okay? So this involves what can be called immediacy and universality. That is that the conservation of momentum holds immediately between these two things regardless of any other matter that's here. And we have to take the field to be universal, or at least to go from here to here. And then eventually, if we're going to use perturbations to estimate masses of other stuff, as Newton hopes can be done and can be done, then you have to extend it as far as you need to do that. Okay? Okay, so another moral. These properties of universal gravitation, this is how Kant thinks of it, I say, qualities of active and passive gravitational mass with inertial mass and therefore with each other. Actually, proportionality is good enough, but let's just call it equality. Universality and immediacy of gravitational force are necessary conditions for Newton's development of what we can call a universally applicable mathematical concept of quantity of matter that can be measured anywhere in the universe. And indeed, it can be shown to be an extension of the traditional measure of quantity of matter based on terrestrial weight, static gravitational weight. Okay? And basically, it's the theory of universal gravitation that makes it possible to talk about weighing the planets by the accelerations of their moon and not making that be ambiguous between what you do when you weigh stuff in a scale here on Earth. Okay? So if you want to have Newton's concept of mass as something that you know how to measure everywhere, you basically do it by assuming these properties of gravitational force. So you want that. So now I ask, so this I've gone through this many times in other writings, and the conclusion at the end has been Kant's got a beef with Newton's attitude toward action at a distance. Okay. So now I ask, what then is Kant's considered view of Newton's abstract treatment of impressed force as a quantity? Now what Newton wants to say is that I don't have to worry about what its cause is, what the mechanism is. Right? Particularly, I don't have to deny there might be some deeper mechanism. I don't have to affirm that there's a deeper mechanism. I just have to treat it as a mathematical magnitude, satisfying the laws which I can deduce from the phenomena governing it. And that's how he handles the mechanical philosophers like Huygens and Leibniz, who said, look, your theory of gravity is fine mathematics, but it's not physics, because it looks like you don't have any cause for it, a proper cause, one that is action by contact. And so you haven't told us anything about the cause. You've just described some mathematical law. And Newton's saying, no, that's a great thing to do, folks. You should be able to do it too. Good luck. All right. So what is his attitude? Is he disagreeing with Newton on this, or is he agreeing with Newton about this? Now I want to say he's agreeing with Newton about this. Why do I say that? Well, there's lots of reasons to say it, but one is what he says in this remark that I started with right before the passage I quoted. He says, one cannot use Newton, the great founder of the theory of attraction, as one's model, if one takes the liberty of substituting an apparent attraction for the true attraction he did assert, and assumes the necessity of an impulsion through impact to explain the phenomena of approach. Yes, Newton thinks you don't have that. Okay? However, Kant says, he rightly abstracted from all hypotheses purporting to answer the question as to the cause of the universal structure of matter. For this question is physical or metaphysical, but not mathematical. That is the cause. So it's enough, as it were, Kant is agreeing with Newton to treat it mathematically. Now, of course, there's a little disagreement with Kant and Newton about this. They both agree about rejecting the mechanical philosophy's strictures. That's very clear. But Kant thinks there's a sense in which we need some metaphysics that Newton doesn't have, and that means for Kant that we need the categories. Substance, causality, community. We have to relate all these concepts to them. Newton doesn't do that. I'm sure you don't want to hear much more about that, except possibly in the discussion period, if ever. So I'm not going to say anything more about that, but basically he's agreeing with Newton in terms of physics. Right? So now what do I want to say? First, Kant accepts Newton's abstract treatment of impressed force as a measurable mathematical magnitude, considered independently of any hypotheses concerning underlying mechanisms. This actually begins with proposition 1 of the Principia. This is the derivation of Kepler's law for any centripetal force, and it's just depending on the geometry of this, where at each point here you're assuming that there's some impulse, whatever the cause might be, that is directed toward the center and that is producing a deviation from the inertial path the body would otherwise hold. That's all we assume. We don't care what produced it. If there is such a thing, there's going to be Kepler's area law holding here. Okay. But, and Kant has a legitimate point here, we must assume that gravitational force in particular, which is a kind of centripetal force, that's the one he really cares about here the most, has what I'm calling the structural properties, that is the mathematical abstract properties, required in order to serve the functions we want it to, including those that facilitate theory-mediated measurements of other centrally important quantities. So here, for example, we're measuring time by the Kepler's area law for any centripetal force. Kahn also has a good point that prominent among these latter quantities that we want to measure, the measurement of which in the theory of universal gravitation involves the direct application of action and reaction, conservation of momentum between arbitrarily distant bodies. Kahn's right about that. Now, maybe there's something going on that explains that. Maybe it isn't going to hold exactly completely when we get to that theory, but it has to hold enough to enable these measurements to take place, or Newton's program has got a problem. The point of this is a crucial philosophical point that I want to make, which is actually related to the discussion we were just having about do you have to have a final ontological theory that kind of explains everything, including all your measurements, or are you going to do something else? And I want to say you're going to do something else. The point of such a structuralist conception doesn't have much to do with what's now called structural realism in philosophy of science. There are two varieties of it, ontic or epistemological. The epistemological version basically says this problem is basically comes out of issues about referential continuity over theory change. And everybody's favorite example has been the ether, starting with Worrell. Okay? So people first thought they were going to explain electromagnetic action and light by this ether that was going to satisfy have some kind of physical setup. It would be somehow mechanical, or it would satisfy fluid mechanics, or it would be elastic, or something, and that would be explanatory of whatever we're coming up with about light and electricity and magnetism. And the idea is, well, that's not going to work because you can't keep those things. But as you go along, the same equations, basically Maxwell's equations, are going to have to be there. And so that's the structural properties of whatever it is that realizes it. And so those persist. And so we are referring uniquely to some property in the world, if you like, that's out there. But we are doing it by structural mathematical properties that allow us to refer to the same thing. So we were always referring, to the Maxwell field in an abstract sense, even when we were building these models of the luminiferous ether. That's what we really meant, or that's what we really referred to. And so we can explain what we did then by Maxwell. Okay. So, and ontic structuralism is even weirder. It says, well, all that really exists are mathematical structures. And that's what we're referring to. Okay. All right. Rather, so it isn't about that. It concerns a methodological use of theory-mediated measurements in ongoing inferences. This is all now George Smith, that are more secure than either inductive arguments, that is curve-fitting plots, or hypothetico-deductive arguments where you posit something and then you try to take it to be the best explanation of the phenomena. Rather, you're using the phenomena to come up with weak, abstract, structural mathematical descriptions of what can be inferred from those phenomena, in some sense, just like from Kepler's laws you can infer inverse square law. You can infer that it has to be either circular, or it has to be a straight line falling toward the thing, or it has to be elliptic, parabolic, or hyperbolic. Okay? So that's just a mathematical fact about such a force. But then, of course, Kepler's laws don't hold exactly. They have to be corrected by various perturbations, because it's not just the sun and the planets that exist. There's all kinds of other stuff. And so that has to be corrected using more gravitational inverse square fields coming from other places. And then you keep doing that and doing that and doing that. And Smith's idea is that what you're doing is getting a much firmer grasp on what you're trying to say about the phenomena, that is, what you're trying to say about nature, than on either of these other two methods. Right? You're not aiming for the ultimate ground level. You're starting with what you can measure and observe now and what you can mathematically say about it. And then if you're going to go deeper, you're going to do it by some kind of delicate corrections to anomalies that are observed in those very phenomena. Now you have second-order phenomena, as it were. You look for anomalies there. And you're always making inferences that are very tightly connected to the phenomena. And you might not even think you're aiming at some ultimate theory. Or maybe you're just aiming at a place where the whole thing would converge and you would not have any anomalies anymore. But that's never going to happen. Okay. Okay, so that's the idea. The greater security of such inferences, this is the Kantian part, is an important part of Kant's disagreement with Hume about causal necessity. Namely, he's saying that it's not just an inductive argument. Hume's right. If it's an inductive argument, you don't know that the future is going to be like the past. All you know is you've observed a bunch of stuff. And the fact that it fits some curve doesn't tell you much. But we want to make a universal claim with our law, at least a tentative one, subject to correction. And that's the source of causal necessity. And I think something, at least a big piece of this, which can be thought of as in George Smith's hands, and this is something Bill Harper's also worked on, as an attempt to flesh out this notion of deduction from the phenomena and the sense in which it is a more rigorous, more secure argument. Right. Okay, next point. These inferences which have this greater security are, of course, not infallible. That's the whole point, really. The less infallible they are, the more secure they are, because you can keep refining them. They're subject to later refinements along dimensions that may become clear only post hoc. Right? So at some point, looking for further gravitational forces, looking for the planet Vulcan, looking for something else, electromagnetic actions, that isn't going to help you with Mercury. And now you've got to go along a completely different place with the velocity of light and so forth, and eventually non-Euclidean space. You couldn't have anticipated that that was going to happen, but that doesn't mean the inferences that Newton made, even the inferences about Mercury, were not very secure. And indeed, if Newton, this is a commonplace, if Newton hadn't made those inferences securely, we would never have any idea about that anomaly, which is only an anomaly relative to what Newton had done. Kant, however, bless his heart, is much less explicit about this process of refinement, and in the end, he's much less open to it than Newton. However, see this part of the Critique of Pure Reason. Don't worry, you don't have to look it up right now. I will show it to you. This is a wonderful passage which is toward the end of the critique in a wonderful section called The Regulative Use of the Ideas of Reason in its Application to Scientific Knowledge, something like that. Okay. And he's talking about the theory of gravitation, one of his favorite examples in the first critique, not just the Metaphysical Foundations, also in the Prolegomena, also in the Transcendental Deduction, if anybody wants to know. You may be skeptical about this. He's talking about, well, we get some unity of the paths of the heavenly bodies. That is, we start off thinking they're circular. We realize, no, ellipse is better. Then we talk about comets. Parabola is better. Eventually, we have hyperbolic orbits, possibly. And then he says, but we further arrive. None of that is causal. It's all kind of kinematic. We then arrive on this path at unity of the cause of all the laws of their motion, that is, gravitation. From there, we afterwards extend our conquest further, seeking also to explain all variations and apparent deviations from these rules, that is, from these orbits, these simple Keplerian orbits, from the same principle, that is, gravitation. So here's the one place that I found where Kant is explicitly acknowledging the importance of these perturbations and of this kind of corrective reasoning. So I say, on that basis, he's got room for that. Not clear that he has room for the law of gravitation being falsified along the way ever. On the other hand, he does think the law of gravitation, unlike, say, the laws of motion, is an empirical law, not an a priori law. So we'll give Kant that, and then we'll move to Einstein, where he has something he can't have. Okay, Einsteinian relativity. This is the 1916 thing. Now, so what I'm going to start to again is Newton's relativity, and just say a couple remarks about how Einstein stands to this. So his version of corollary 5, that is Galilean relativity, is changed mathematically by replacing the Galilean with the Lorentz transformations. From a geometrical point of view, we use a four-dimensional space-time, this is now the Minkowski, in which the light cone, not the planes of simultaneity, are invariant. Okay, special relativity. Corollary 6, gravity is no longer an impressed force. This is some kind of version of the principle of equivalence that seems to hold. It is represented by a four-dimensional affine connection with variable curvature, dependent on the distribution of mass energy. Furthermore, it is not in general possible to split that affine connection into inertial part and have inertial frames, gravitational part, which would be the potential in an inertial frame. Okay. Now I want to talk more about this one. And here we're going to bring in the Newton-Cartan spacetime, which you heard so much about today. I'm a little embarrassed to put up this picture from my 1983 book. Compared to what I did in that book, what people are doing now is so far beyond that, which is on the one hand embarrassing, on the other hand it gives me great hope for the future. But you already know about this. And since I'm not going to do any calculations at all, I'm not even going to have any indices, I'm just going to write the generally covariant equation this way. So this is the covariant Poisson equation, as you already heard. This is the Ricci tensor, and so forth. Here I have kappa instead of big G, just to make it the notation fit general relativity a little bit better. And also from choice of units here, I've got a negative sign. And here I have a rather simple-minded, really a really schematic, not a picture of a real physical situation of what you have. Suppose we start with ordinary flat space-time, Newtonian gravity. So you do have inertial frames and bodies, as it were, not moving under even gravitational force. Right? And then you think of it, then you think of the free falls in that space-time. Well, you can take those free falls also to follow geodesics in the space-time, basically because of the acceleration field property. That is, there are these trajectories that are independent of the mass or the other properties of those bodies that might be following them, and that defines a class of geodesics, four-dimensional geodesics, and therefore an affine structure. Okay. And then you've got stuff that isn't either inertial or gravitational freefall. That would be an arbitrary accelerating thing, say a body moving under electromagnetism or some such thing. Right? Now, if you don't start with the flat connection, but you start with the non-flat connection in this equation, then you can ask the question, well, one thing you can say is, unlike in GR, the affine structure is variably curved, that is the four-dimensional geodesic structure, not flat, but the spatial and temporal metrics remain flat anyway. So there's not that strong coupling between the two, basically because of the degeneracy of their geometrical objects relative to the connection. Okay. But the second thing is that the no splitting thing also holds as long as you're not in an so-called island universe, which would be an isolated system. So suppose this is the center of mass of the solar system, and suppose the solar system is the only thing there is. So now you have corollary 6. This is an inertial frame. And actually, you don't even need corollary 6 because there's nothing outside of it. But if there is something outside of it, you can apply corollary 6. You can take it to be a local inertial frame or an approximately inertial frame. But unless there's some isolated system of matter somewhere so that the thing is going to be asymptotically flat, you're not going to be able to split it uniquely into a flat connection, which would be, say, a center of mass frame, and the gravitational potential. There's going to be an arbitrariness there. So in that sense, the principle of equivalence is satisfied here. Now what I want to talk about is, okay, that's fine. And now I want to think about the crucial differences between Newton-Cartan space-time version of corollary 6, and therefore equivalence, and the one in general relativity. And that basically has to do with the things I was just saying, that this is quite a different structure than what you have with light cones. So it's really special relativity, the combination of this view of gravitation with special relativity that makes GR what it is. So the geometrized version of corollary 6 is not what is essential to full Einsteinian relativity, that is general relativity. It is rather the combination I just mentioned. And again, I've just changed corollary 6 so that it really fits the Newtonian case. That's just as true there, as long as it's not an island universe. And so that's not enough yet to get GR. So the way you go to GR is you have to go through Maxwell. Okay. So now let's look at the Maxwell field. And I want to say that the Maxwell field, and this is going back to the structural realism business, like Newtonian gravitational field, is an abstract mathematical structure, if you like, or it's represented by one. And that's all we need to say about it. As Hertz said, Maxwell's theory is Maxwell's equations, or rather what Maxwell's theory is about is the field that satisfies them. But unlike the Newtonian gravitational force, the Maxwell field is dynamical. That is, it's not propagated instantaneously and as it were rigidly. It's propagated through space and time with a definite finite velocity c. It is thus an actor in the physical world along with the matter upon which it acts. Again, Howard Stein's terminology. That's not true of the Newtonian field. The actors are the masses, and the field is a way of describing their interactions. Action and reaction holds between them, not between them and the field. Okay? So that's a crucial difference. but it still has this abstract quality. And then I'll just put this up. This is the electromagnetic spectrum because I want to show you Hertz's experiments with radio waves. That's the visible part and so on. So from the Maxwell point of view, you get this wider picture of electromagnetic field. Light is just a part of it, but it's always velocity c and so forth. So now we have Hertz's experiments with radio waves, and what I'm saying is these experiments establish, and I'll tell you what I mean by that, securely establish these structural properties of the Maxwell field via theoreated measurements of things like refraction and reflection of the radio waves, just as the corresponding properties of gravitational force are similarly established in the Newtonian method. What do I mean by established? I don't mean it proves everything about them. What I mean is it's established like saying, you know, a certain church has now been established, or a certain government has been established. That is, we've got something going, right? So what's going is empirically now, not just mathematically, is, if you like, the empirical reality of the Maxwell field. And we have reason to continue making other kinds of experiments and measurements on it to establish more and more of the properties of that field until again we run into some problem and we have to do QED or who knows what. Or we have to at least add Lorentz's theory of the electron. Okay? So established doesn't mean proved to be true. It means get it going so that it makes sense to treat it as real from the point of view of this epistemic process. It's a good idea to keep on going this way. Okay, so what about special relativity? This is a familiar story. The light cone is not Galilean invariant, obviously, because the velocity of light under Galilean transformations is going to change from inertial frame to inertial frame. So the structural properties of Maxwellian causality, that is finitely propagated a la the Maxwell field, are in fundamental tension with those of Newtonian, instantly propagated gravitational causality. There's a big problem here. That's just another way of saying what was already said yesterday. And I think it was said by John and maybe others. Okay. So what do? Well, we say the light cone is the fundamental structure, not the simultaneity planes. Space-time itself is Lorentz invariant. Not only is the Maxwell field Lorentz invariant, but so is space and time, if you like. The structural properties of Maxwellian finitely propagated causality are also those of the fundamental kinematics of motion in space and time. So all this is a similar kind of structural theory-made measurement correction model of what you're doing. Okay, so interferometer experiments of Michelson, Morley et al. I say et al. Because this is actually the apparatus of Morley and Miller, I think in the years 1902, 1905. I see on Google anyway that it's alleged, and John can verify this, and others can, that these were especially picked up on by Einstein in 1905. Appealed to. Good, they were. Well, you can't trust Wikipedia, right? Okay. So anyway, this is Morley and Miller's apparatus. And I basically put that there not up because of Einstein, because if you look on Google Images to the original Michelson-Morley thing of it, you find it, but it's a horrible picture, so I found a better one. So what I'm saying, these interferometer experiments, whenever they happen, establish these structural properties of spatiotemporal kinematics relative to the Maxwell field in the same sense that the corresponding properties of the Maxwell field are established by Hertz. Not proving that they're real for all time, but establishing that that's the way to go, at least for now. And that's what Einstein did. Okay, now we go to GR. Here I have, again, a not completely happy thing taken from Gauroche's book, where I have neglected to show the light cones tilting toward the black hole outside of it. So again, that's a schematic part. This part's not bad, though. So what it's showing, basically, this is a nice picture because it shows how the changes that happen in the light cone are basically determining all the changes that are happening in the gravitational field. That is in the affine structure. The affine structure is determined by the light cone structure, unlike in special relativity. Space-time is infinitesimally Lorentzian, that is in the tangent spaces. This is now Einstein's equation. I've got big G here, which is why we've got kappa here. And we have this 8 pi so that we can get the Poisson equation, this being the stress energy tensor that you already have heard about. Okay, I'm almost done. Now I want to say something about this limit, and again, this is going to be pretty elementary compared to what Carla told you about these limits, but it's really that very idea. you want to show something like this, the Newtonian limit. Looks kind of strange, but actually you can do that. And one of the things you have to do, and I think Carla explained it, is here this is also a slight variant of the Ricci tensor, which is varied by putting in the curvature scalar in order to make it satisfy a conservation law, since we have t here. But the Ricci tensor is here. And this here we have dt, which is going to be the time metric. And that's going to be just the g metric of the space-time. Okay? And this is going to be something, we can think of it as a C infinity limit. And what we do is we have a manifold, and we consider a family of models on that manifold of Einstein's field equation, which are indexed by a real parameter. That's the lambda that Carla told you about, such that at each point of the manifold, the light cones at that point are successively expanding relative to the earlier ones. That is, the earlier ones lie, if you like, in the time-like part of the later one. Okay? So that's all that you really have to assume, and you have to think of it that they're becoming tangent in the limit to a space-like hypersurface, which is going to be connected to some observer. The proof is then that the limiting structure is a model of the Newton-Cartan theory. And various people, including Ehlers and others, were working on that all in the late 70s and around 1980. And one interesting thing about this situation, tension to which was first called by David Malamud, is that if you think of it that way, the limiting process, without any further assumptions about Newton-Cartan spacetime, which are often made to ensure spatial flatness, and if you like, temporal flatness, but it's really just the fact that you're getting the Ricci tensor that is all you need, thereby forces the geometry on each such space-like hypersurface to be Euclidean space. So that's kind of cool. So now I want to just say a little bit coming out of this, and I'll be done. So here we have the kind of standard picture. This is from Misner, Thorne, and Wheeler of the of some kind of Schwarzschild field here around the sun. Okay. And what this picture shows is just the three-dimensional part. And here they emphasize that. And here you show the three-dimensional bending because you have a space-time of variable curvature, kind of a hyperbolic structure. And so the geodesics are, dipping down into that well. And that's going to explain the deviation. And it's part of the three-dimensional geometry. And here, I don't know if you can quite read it, but Misner, Thorne, and Wheeler say the ray of light pursues geodesics, but geometry in which it travels is curved rather than flat. Parentheses. Actual travel takes place in space-time rather than flat space. Correct deflection is twice that given by the above elementary picture. So if you take account of the curvature of the connection as well as the curvature, if you like, of the projection of the geodesics down onto this hypersurface, then the thing is double. Now, I don't actually know if about what I'm going to say is true, but why I got struck by this is that when the bending of light experiments were done, the Einstein deflection was actually tested not against no deflection, but against the Newtonian deflection that had, I think, been derived already in the late 18th century by somebody, whereby you assume light is a particle, you assume it has very small mass, you imagine the mass getting smaller and smaller, take it to have a finite velocity, but a very fast one, which of course was well known to Newton and the Newtonians, and you derive half the correction of the GR correction. So the real crucial test is to show that you got twice that, right? So now we think of what's missing here is the connection curvature, and what you have to add is the projection onto a curved flat space to get the correct double curvature. So 2 times 1 is equal to 2, 1 plus 1 is equal to 2. So I infer that maybe that's the crucial difference between the Einstein-Cartan theory, the Newton-Cartan theory, which after all is going to give you the same prediction if you do something like this in it, the same deflection as the traditional Newtonian deflection and the real GR deflection. It looks like the difference is going to be, I can't say this is true, but I kind of get the idea that the extra thing is the spatial curvature. All right, so enough of that. Last slide. We also have an experiment and then a whole bunch of experiments to confirm this. This is the 1919 experiments. This is the picture in Sobral, Brazil, as opposed to the one in Africa over here. This is actually from the London Times of sometime in 1919, and they have a picture of the deflection. Here you see the little observatory in Sobral, Brazil, and here's a picture of it with its telescope and its camera and the mirrors. Okay. So what I say is, observations and photographic measurements establish these structural relations between Einsteinian and Newtonian gravity, the ones I was just talking about with the limit, in the same sense as in the previous experiments. That is, they give us a reason to say, yeah, that is the right way of thinking of Newtonian gravity vis-a-vis Einsteinian gravity. And this experiment is, as it were, giving empirical reality for the first time, in that sense establishing that those structures are in the phenomena, at least so far. And then, of course, we make more and more precise things of this. We do the Mercury thing, which is more complicated, and so forth. Okay, so I'll stop here.